All right, moving on to problem 14, part A from the final exam practice. We want to find the area enclosed by this curve, C, defined here, and also we want to find the length of this curve, C. So let's deal with area first. So the area, A, is equal to the absolute value, integral of 0 to 1. So we do absolute value just so we don't have to figure out which is the leftmost endpoint. And then we're going to be integrating y dx essentially. So this these bounds are a little bit weird the way that I'm writing them, but I'll clarify in just a second. So this is the absolute value, integral of 0 to 1 of 1/2 t squared. So this is my y, and my dx is now just the derivative of x with respect to t, and then times dt. So this will be, so I differentiate x with respect to t, so I get dx is equal to dx dt times dt. And so when I differentiate this function, I'll bring the 5/2 down, it'll cancel with the 2/5, and I'll get t to the power 3/2. And then times dt, and we're taking the absolute value of this expression. Okay, so this is equal to absolute value, we'll keep that, 1/2 integral of, from 0 to 1, of t to the power 2 times t to the power 3/2. So this would be 4/2 plus 3/2, so this is t to the 7/2 with respect to t. And this is equal to 1/2. So now I want to integrate t to the 7/2, so I find the antiderivative. So I add 1 to the power, I get t to the 9/2. And then I multiply by 2/9, right? Divide by the power is the same as multiplying by the reciprocal here. And I'm evaluating at 1 and at 0. And then I'm taking absolute values, but you probably see at this point that I actually do not need these absolute values. But either way, I'll write this out. I have 1/2 times 2/9. And then I evaluate at t equals 1, so 1 to the power 9 is of course just 1, 1 to the power 9/2. Either way, 1 to any power is just 1. So this 2/9 is multiplied by 1, and then for this term at t equals 0, well, it actually contributes nothing to the value of the integral, because that term is just 0. So this is the value of my integral. 1/2 is going to cancel with the factor of 2 in the numerator there, and so I get that the area under this curve is equal to 1/9. All right, so 1/9 for the area. Now how about for the length? So the length is equal to this integral, so it's L is equal to integral of ds, right? Ooh. Well, you know, sometimes you say one thing and write another, but either way, integral of ds, right? Not square root, either way, forget about that. Integral of ds. And so ds is the differential of our arc length, and so for a parametric curve like this, the differential of the arc length is the square root of dx by dt squared plus dy by dt squared square root times dt. And so I want to compute all of this stuff first, so I'll figure out what ds is equal to, and then I'll plug it into my integral, and then I'll evaluate this integral from 0 to 1, even though this is a little bit misleading writing it out like that. But either way, I know I'm evaluating the integral from t equals 0 to t equals 1. So what we want to do is just, well, first of all, before I even write what this expression is equal to, I need to know what dx by dt and dy by dt are equal to. So I computed dx by dt up here, so I'll just remind you what we got for that expression. So dx dt was, of course, the derivative of x with respect to t, and this was t to the power 3/2. Cool. And dy by dt is also pretty easy to differentiate. It's 1/2 t to the power 2, so I bring the power 2 down, cancels with 1/2. I just get left with t. And so now I can write out my differential for the arc length. So it's square root of t to the power 3 over 2 squared plus t squared. Take the square root of this and integrate with respect to t ultimately. But either way, this leaves me with square root of t cubed, right? So I just multiply my power by 2, so 3 over 2 times 2 is just 3, and then plus t squared, all times dt. And so here I have a common factor of t squared, so t is positive in this case, so then the square root of t squared, so I'll first write it like square root of t squared, but that'll just be equal to t. I'm left with t plus 1 inside this square root. And ultimately, I can just write this as t times t plus 1 square root dt. Okay, so this is the differential of my arc length, and so now to find the length, I just need to integrate from 0 to 1, t square root of t plus 1 times dt. And so to compute this integral, I'm going to do a change of variables. I'll do a substitution. So I'll set this equal to t plus 1. In that case, subtracting 1 from both sides, t is equal to u minus 1. So either way, you can see that du is equal to dt. And so I'll go ahead and just make this substitution. That will turn my integral into so at t equals 0, u is equal to 1. At t equals 1, u is equal to 2. And so now I'm integrating from 1 to 2 of u minus 1, because this is our t, times square root of u, but I'll write that as u to the power 1/2 du. Okay, and so then multiplying everything in my integrand, this is just integral from 1 to 2 of u to the power 3 over 2 minus u to the power 1/2 with respect to u. And so now I can integrate this. The first term is going to be 2 over 5 u to the power 5 over 2, so adding 1 to my power and then dividing by that, and then minus 2 over 3 u to the power 3 over 2. I evaluate this at 2 and at 1, and what I get is 1/12 rad 2 over 15 minus a negative, so I'll put plus 4 over 15. And so this is my final answer for this length. And if you want a numerical approximation, so not the exact answer, this is approximately equal to 10.83. Okay, so either way, I would prefer the exact answer, but this is, also a nice approximation. All right, so that ends 14A for us.